So this topic is about also one of the important topics and also applications in let's say VR and AI is about monocular SLAM system. Yeah, I think they introduced a new concept of method called spatial semantic graph. I will believe it is also quite related to the previous presentations about semantic segmentation, maybe. Yeah. Then let's dive into your presentation. Yeah.
Okay, thank you for your introduction. And I'm Zezi Xu from Shanghai Jiaotong University. And it's my honor to give my speech, the Spatial Semantic Graph Enhanced Monocular SLAM System. And we'll go through from the introduction. Modern simultaneous localization and mapping systems, also known as SLAM systems, plays as an important role for augmented reality or virtual reality. Applications could understand environment through SLAM or get poses to display things and even enable interaction among virtual and real objects, such as in this video. Those are about semantics and pose estimation. And AR needs object poses to display things. However, recent object SLAM cares more about trajectories, which means the poses of the camera. As we can see in this video, those objects should be on the same plane, as you can see, and the virtual fluids should be trapped. The poses on the left are not accurate enough, so the interaction is wrongly computed. So in this paper, we try to provide better estimation of object poses by introducing more semantics, as we mentioned in the title, the spatial semantics. Before we move on, there is a little story. One afternoon on the way to the campus, I tried to imitate as a semantic SLAM system exploring the environment. While exploring, I realized besides locating myself through the semantic objects in the environment, I could also infer lots of things. For example, there should be a big stone behind that tree, even I can't see it, or two doors should be on the same plane, or the car is on the ground, or one thing is placed on another. Those are the relations between objects, either physical or spatial, that leads to the perception and the inference above. Those relations must be a part of the semantics, which should not be ignored, and could be introduced to a semantic SLAM system. So the SSC SLAM proposed in this paper is an attempt to do this. Recent years, semantics are introduced into a SLAM system mainly for eliminating moving key points or improving robustness. For example, dynamic SLAM uses neural networks to recognize potential dynamic objects and eliminate the changing foreground so that the map will condense points which are likely to be static. And there are also works who take care of dynamic objects and build data associations among them, such as Yang's work, a cube SLAM. But most works introduce objects themselves as semantics, and in those works, relations among key points are imposed by the object labels to improve the accuracy of poses. And similarly, the relations among the objects should also be considered to improve the estimation of object poses, but are often ignored. Some recent works have introduced one type of spatial relations, posing that uses quadrics to represent objects and detect infinite planes in their systems. And for the first time, a tangency constraint modeling that an object is supported by a plane is introduced, and their work outperformed its baseline system using RGBD sensors. Then, Yang utilized that constraint into a monocular system and achieved better results. However, both works are limited to a certain type of relation and fail to explore more or to explicitly reconstruct those relations as output. There are also approaches try to build voxel maps with semantics. For example, Yang's work combines SLAM with CRF inference to get voxel map and label each voxel with an object class. Although it provides good labeling at the level of voxel, the object level semantics, such as spatial relations, is lost. And in fact, spatial relations has long been exploited in other fields, such as a geographical information system, GIS system, or in the field of relocalization, layout inferencing, and extra. So come back to the Floyd's demo. In the left part is Doran's work, and Doran's work had integrated semantics and detection structures, but the objects detected are often not strictly aligned, causing gaps and holes. And that makes the AR fluids rendered in unexpected ways. So in this paper, we're going to design a data structure to represent the semantics, including objects themselves and the relations among them. Then we're going to show how the spatial relations will improve the estimation of objects' poses. The first part is about SSG, the spatial semantic graph. SSG, of course, is a graphical data structure. It is directed, and the vertices or nodes are the semantic objects or derived planes. And well, the edges are the spatial relations connecting the related vertices. Using SSG, the spatial relations among objects could be clearly organized. As shown in figure 1, a cuboid is supporting a cylinder, as well as being coplanar with another cuboid, and besides another object is hung on the wall. And in SSG, those objects are the nodes or the vertices, and the spatial relations among them together are the spatial relations, and the objects and their spatial relations together form the higher level semantics of the scene. And there are also many properties such as the poses, scales, and the upright directions for the vertices. And there are also two kinds of objects. The hangable objects means those objects are always hung on a wall. And the normal type object means this kind of object are always placed on horizontal planes. Until now, we could notice that the design of spatial relations determines the expressiveness of SSG. Here, we selected some common yet representative spatial relations based on several widely applied assumptions in human-made environment. The first assumption is that the static object should be supported by or hang on something to cancel the gravity. And the second is the structural planes are either horizontally or vertically aligned, also known as the structural environment assumption. And based on that, we notice some of the relations are directional. For example, if a picture is hung on a wall or a cup is supported by a table, those relations really cannot hold after exchanging the relatum and the referent, such as a wall is hung on a picture. That does not work. So this kind of relations are directional relations. And there are some bidirectional relations, such as the cup and the toy are both observed by camera, or they are both placed on the same table. And those relations will still hold even the order of the objects is changed. And we define several relations. For example, the supported by object relation defines that an object is supported by another vertically, such as a cup is supported by a book. And this relation is very common to see in our daily life, and usually has the contact surfaces. And supported by plane is similar to the supported by object. And the hang-on plane is specially defined for the vertical objects, the hangable objects, which could be found on the walls. And co-observed edge is built when two objects are observed at the same time. As this relation is regarded as the neutral type in our system because it's tightly coupled with the camera's observations. Other relations will be inferred only if a co-observed edge exists between those objects, and this design avoids a highly connected graph that consumes lots of resources. Therefore, SSC maintains good locality and could be split and organized at low cost. And the coplanar horizontal, I described two objects are coplanar, and they're also coplanar vertical. It's not drawn here, but they work in a similar way. And all the relations defined above are summarized in table 1. And by the way, besides all those, one could define more relations, such as an object is containing another, or object is linked to another, or an object is attached to another by a magnetic field. More relations means more powerful graph, and it could describe a more complex thing. It just depends on your needs or the applications. So now we're going to do some inference with those relations. It could be noticed that the bidirectional relations exist when two objects have common directional relations to a third one. Often the third ones are not detected or not known yet. That inspires us to use the bidirectional relations to infer the existence of the third one. So in our graph setting, when we found two coplanar objects, we believe there's a plane supporting them. So those planes are called derived planes. The derived planes is not detected directly, but it is inferred from the bidirectional relations. So they are called derived planes. And they will be added to the graphs as the nodes or the vertices and has directional relations to those objects. Also, SSC involves during runtime, and the procedure is demonstrated in figure 3, but I prefer video. First, newly detected objects will be wrapped into new vertices and added into the graph. And meanwhile, some objects are observed at the same time, and co-observed edges are added among them. And next, the edge inference function will check each co-observed edge and try to find if the object it connects have any other relations. If a more specific relation is found, it will replace a new relation edge. And finally, the planar inference function will check each object if it is supported by another. If not, it will search for the coplanar edges. If one of the neighbors is already supported by something, the function will create similar relations for the rest objects. Otherwise, it will take all those coplanar objects to propose a new one and insert that plane into the graph as a vertex. Then the relations between objects in the plane are modeled as the supported by plane relations. Now we try to apply the SST into an instance level object SLAM system. Our main contribution is to include semantic constraints provided by SSC in the bundle adjustment procedures. You can notice that some spatial relations could provide constraints, such as coplanar relations, or they require the object's bottoms are on the same plane, or the supported by objects requires one's bottom is touching another's top. So as we can see in figure 3b, at the right of the screen, the factor graph shows exactly what we have done. The traditional object SLAM system, SLAM system group the key points through the object labels and apply some geometry constraints, and that will lead to a better estimation of the key points. However, we directly add constraints among the objects that provides the potentials to improve, that provide the potential to improve the estimation of objects poses. And the overall pipeline is shown in here in the figure 3a. For AR applications, sometimes they need to understand the specific information of objects and acquire high-precision models to perform interaction between virtual and real objects. So we concentrate on instance-level SLAM system, which could benefit from predefined object models. The whole system is based on Doran's work and implemented on the OP-SLAM. So as we can see, the introduced SSG could organize the didactic semantics while providing new constraints to the system. We summarize two types of constraints. One is distance constraint, while another is direction constraint. They will together constrain the pose of the objects. We assume those error terms are normally distributed and try to minimize the robust objective function during bundle adjustment. And here the CSR is a spatial relation term, while the CG is a traditional geometric term. And while the system is running as a serial analysis of spatial relations among objects, and based on analysis, new constraints are added, and this equation is minimized during the following BAs. Now the evaluations. Our system has been implemented in C++ and deployed on a Linux machine. Made our own SSC dataset, and it provides pre-built object models a sequence with markers to provide ground truth of objects' poses, and a sequence without markers for visual tests and results. We perform quantitative evaluations on SC dataset using our SSG SLAM against Doran's work and ORB SLAM. We first check the impact on the trajectory accuracy. ORB SLAM's results have already been rescaled and aligned to the origin. We evaluate the root mean square error on the absolute post error. The results are in table 2. As we can notice, in the long sequence with larger things, our approach achieves smaller APE without loop closure module. Here, the objects and semantic constraints help to correct the scale drift, and that indicates in the scene without loops, semantics helps to improve systems. However, the advantage is not significant in short videos, which is in our expectations. The number of semantic constraints is way smaller than the reprojection constraints, and that makes it hard to influence the trajectory. We then evaluate the estimation on object poses, the core part. The detailed evaluation are shown in table 3. In general, our system gets more accurate object poses estimation in the baseline. You can see that. And for further analysis, we separately record the RPE for each axis. We found it interesting that on y-axis direction, our system is much better, while the improvement is not that significant in other directions. That means in SSC dataset, most spatial relations are vertical. Thus, those results are interpretable. To compare in an intuitive way, a scene is shown in the figure 5, as can be seen. The baseline systems objects won't align because of the measurement errors, while the SSC SLAM corrects that and achieves good reader qualities. We also got a video here. In a summary, our approach is more accurate on object poses in the baseline, and will slightly improves the accuracy of camera trajectory. To fully investigate how assets work in the runtime, we keep track of some important metrics. In figure 6a, we record the variations of the number of relations, the semantic constraints, and the SSG involving time. The blue one is the spatial relations, and the red one is the semantic constraints. As the time proceeds, the scale of the graph grows, while the SSG evolving time rises up slightly. And thanks to the group locality, SSG really works on a small group of nodes and edges, just in the neighborhood. We then set limitations on amount in the figure 6b. We set limitations on amount of constraints. The figure 6b shows that as more semantic constraints are applied, the estimation of the camera and objects are improved in the video 6. Okay, we have also performed evaluations on cost of time. The tracking thread achieves around 25 FPS, while SSG introduced little overhead to the system. However, the performance of our system depends on the quality of SSG. So if there are few relations detected, as simulated in the figure 6b, when there's no constraints, our system degrades to the baseline. Also, there could be wrong detections, such as shown in the figure 8. And after running the videos for more than 10 times, around 6% of the relations could not be found or wrongly inferred. And we also have a visual qualitative evaluation. For AR applications, the collision among virtual and real objects could be wrongly detected with bad estimation, which causes inconsistency. And then figure 7 shows that. And then just come back to the demo. The 6 objects placed on the same table together build a valley. The virtual rings are poured from the sky and are expected to be trapped in that valley. However, using poses provided by the baseline system, without SSG, the objects have holes under them. So in the left part of it, the flood has run through the mountains. And in the 7b, after SSG is introduced, the coplanar relations make sure that the objects are placed on the same plane and the water is blocked as expected. So in this paper, we propose SSG SLAM to provide more accurate estimation of object poses. And SST and the semantic constraint provided by it are the core idea of our approach. An SST is designed to describe and organize detected objects and the spatial relations among them. And it could organize the scene in an abstract way while providing semantic constraints for SST SLAM. And evaluation shows that in general, our approach achieves better results. And it is obvious that the SST is not fully exploited. New spatial relations could be defined while new constraints could be applied. And the semantics in SST could also be used by applications to understand the thing. In the future, we are interested in more robust spatial relation inference approaches, leveraging neural networks and exploring more functions of SST. For example, 3 weeks ago, we used the SST to store the whole map to decrease the data usage, and the graphical data structure may provide some other kind of functions. We are interested in that in the future. And here is an end video, and I think that shouldn't. In fact, it's the end of my speech. Thanks you all for the listening. Who is interested could see that video, but the Q&A could just start from here.
Okay, I think Professor Daniel, you turned on your audio, right? I think you are prepared to ask questions. Or hello, Professor Daniel.
I have a question. I saw that in the review of your paper, there was one reviewer who was saying that you should cite 2 papers, one from CASA in 2018 and one from CAS, which is the journal where the proceedings of the conference are published. I just saw that in your new version, which is in the journal, you didn't take account of the reviewers' comments. These 2 papers are not cited. Could you explain why you didn't cite them? Do you think they are not related to your work?
After I read those 2 papers, I found that it's not so related to my work, because one is a bit little further, and I cannot very remember the contents of the 2 papers. But when I just include the papers in my citation list, reference list, but I didn't cite it in my paper, and the journal wants me to just eliminate that 2 papers, so I just removed that 2 papers. So I don't know.
I find this a little strange, because one I can understand, but the second one, which was on SLAM, I saw that the reviewer was right to think that it should be cited. So I think it was a mistake not to cite it.
So sorry for that.
Okay.
Yeah, I agree with Daniel. Yeah, you should take the comments from the reviewers more seriously. Yes, it's always nice to you know, to consider the reviewers' comments. Yeah. But except for that, I think the presentation is good. Especially, I think the fluid example is nice to explain your novelty. I think the supporting playing, yeah, the concept. Yeah. If there is no more questions from the audience, then maybe we can keep home to our next.
Yeah, I have one question.
All right. Okay. Yeah,
yes.
Please.
Shiwi.
Yes. Yeah.
I have one question. I would like to know if you have seen of any application to your SLAM methods, and if yes, how far it is better than the others.
Currently, there are projects going on, and it is applied in that kind of in a project, but it is a little bit and it can't be appealed to the public for now. So, but
in which area? In which area? Because in fact, it's a map.
it's just used in augmented reality and the virtual reality. This project is just focusing on to some AR things, and there is a need to acquire the better estimation of the object poses. So we try to dig into that and come up with this spatial semantic graph things. Yes.
Okay. Sorry, Shihui, can I just ask a quick question here, Shihui? Yeah. Okay, Zezi, I think I like your presentation. It's pretty good. It's clear, and but I got a question regarding the technical questions. And you talk about different relationship among the objects. For example, object supported by object and supported by plane. For me, these two looks very similar. Perhaps you just need one. Yeah. So I don't see the reason why you need these two. And this is the first question. Second question, and your semantic, talk about semantic, the one difficulty actually is about occlusion. Often in the complex thing, environment, you may have the object, overlapping or and occluded, by each other. So do you think your algorithm can handle that situation as well?
Okay, for the first question, we need a supported by plane relation because we didn't have a plane detection algorithm integrated in our system. And all the planes in our system are derived planes that is inferred from the bidirectional relations. So supported by plane, the plane is actually the virtual plane, not detected planes. So that kind of that relations is differently processed in our system. So that is necessary, at least in my design, yes. And for the second question, for SLAM system, it's a dynamic system. You will carry a camera or other sensors to explore the whole scenery. So for the overlapping and the occlusion things, it could be solved by accumulating all the evidence or the cues when you are exploring the sceneries. So as far as I can see, it's not so big a problem, maybe.
Have you tried, back to the Nadia's question, have you tried to apply your system to the robotic? SLAM, most, obvious application for the SLAM is for the robotic system. So do you think like your algorithm can be applied to the robotic system as well?
I know I haven't tried it because it's originally designed for the AR system, and for the robotics, maybe there are other things they could do, or because they can have more sensors to get integrated, and maybe they can the more sensors maybe lead to more accurate results for at least for the robots themselves. Yes, I didn't try it, so I don't know. Yes.
Okay, thank you very much. Okay, yeah.
Yes, thank you for the questions.
Yeah.